one.
Okay, so yeah, we were at this point के अब हमें बस area of a triangle use करना है, जो हमारे पास क्या होता है, we have area of a triangle, ये triangle मैंने बनाया है, right? Okay, so this is equal to 1 by 2 times the base of the triangle times the height of the triangle. So if I use this now, so well, it follows immediately कि हमारे पास जो the area है which is swept out in some delta t, that would be equal to 1 by 2 r square times delta theta. Again, we used the aid of this diagram to find the base and the height for this thin triangle BSC. Okay. Now the next step is simply to we can multiply and divide this thing with a delta t, and what that gives me is 1 by 2 r squared omega delta t, right? Because d theta over dt, or delta theta over delta t, would be omega, right? Now the next step is to recall के the angular momentum जो है वो क्या होगा आपके planet का, it would be L, which is equal to m r, a perpendicular velocity, right? Which I can write down as m r times r square हो जाएगा and omega, right? Because perpendicular velocity is just r times omega. So if I use this in this above equation, so what I have is my this dA over dt would be equal to 1 by 2 r squared omega, and let's multiply and divide this with the mass. So I can now, using this thing, I can write this as ye wala m r squared or omega, this makes up L divided by well ye 2m रह गया बस, तो 2m, right? So from this we can see कि हमारी जो aerial velocity है, इस चीज को हम aerial velocity कहेंगे, this is equal to L over 2m. So it's directly proportional to angular momentum. So let me just write this as a dt is directly proportional to the angular momentum of the planet. So well, Newton's laws जो है वो हमें बताते हैं कि जो rate of change of angular momentum है, that is equal to the torque of what, of the forces that are acting on the system. So for a planet that is orbiting the sun, that torque is 0. Why is it 0? Well, because क्योंकि the only force that is acting on the planet is the force of gravity, and it acts in the line from the planet towards the center of the sun, right? So and so that means that it has the torque is 0, or we can say that it has no leverage about that central planet, right? So we can say the planet's angular momentum about that point must remain invariant or constant, right? So with this, then well, consequently, the rate at which this area is swept out is also a constant, right? This thing, and so that's what the Kepler's second law was telling you, right? If you go back up here, if you read this second law, I'm not going to read it again, you can just refer to it here. So we have well, we have proven Kepler's second law as well. Right. Now, finally, let's move on to the third law of Kepler, which you can see what does it say कि जो हमारे पास time period squared है, it is proportional to the cube of the semi-major axis, right? So let's go down first of all, down, 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 and here, and let me, मैंने इसके लिए कैसे लिखा था? Kepler's second law. Let me just write Kepler's third law. Right. Okay. So again, अभी हमने देखा है कि the rate of sweeping out the area is equal to L over 2m, right? And the area of an ellipse from geometry, right, is given by pi times a times b. So we can now write from this that the time for a complete orbit would be what? Well, we know कि a over t, ये अभी जो हमने ऊपर equation देखी है, it is equal to L over 2m, right? So from this we can write कि जो t है, the time period would be 2 pi times ab over L, right? Or now here we would also be needing the solution जो हमने ऊपर निकाला था for u, which was, if I go back, which was this thing, ये वाली चीज, right? So let's just copy paste this. Okay, I think इधर कर लेते हैं थोड़ा सा, right? ठीक है. So we have this thing, और हमें पता है कि ये किसके इक्वल होगा? 1 over r के, because u, we defined u as 1 over r. And well, actually I should have copy pasted the equation for the ellipse as well. वो क्या है हमारे पास? ये है, right? So let's just bring this down as well. Let's go down, down, down. Yeah. ठीक. Now what we have to do is we just have to play a game of comparing, right? So if I compare these two equations, what I can do is I can write this L squared over g m squared from this above equation. इसको मैं फिलहाल 1 कह देता हूँ, इसको 2 कह देता हूँ, from equation 1, and this thing would simply be equal to it would be equal to a times 1 minus e squared, ये दूसरी equation से, right? So now we have this thing. We just need to figure out what would the value for b in this जो हमने put करनी है वो क्या होगी. तो उसके लिए let me just quickly again draw an ellipse. ये तो line बन गई है. Let me draw an ellipse. Hopefully this works. Yeah. Okay, and let me draw its axes, something like this. And let's call this top wala point जो है इसको हम B कह देते हैं, for no good reason, right? But let's just call it B. And we would have one of the focus would be over here, and let's just call it F1. And the other one would be over here. We would probably not even be needing that, but let's call it F2. And let's call this center O, और ये वाला जो distance होता है ये AE होगा, and this distance, this one is A, और यहाँ से इसके ये bottom तक जो distance होता है वो हमारे पास B होता है, yeah, B होता है. And now the top point B of the semi minor axis of the ellipse is exactly A, this one. तो from A from F1, right? So then we can use the Pythagoras theorem, and we can find the value of B, or using the Pythagoras theorem, B squared हमारे पास आएगा A squared, right? This one minus इस वाली चीज का squared, so that would be A squared E squared. And what I can do is I can factor out A squared, and I'm left with 1 minus E squared. So that's B, or at least that's B squared, right? So if I go back over here, मेरे पास t की ये वाली equation थी, अब मैंने बस इसके अंदर substitutions करनी है basically. First of all, I will square this equation, ठीक है? So let me write it down. T squared would be equal to 2m pi a times b whole squared over L squared. Right, now I just have to plug in some values. यहाँ से मेरे पास L square के लिए ये वाली equation है. From this I can easily see what L squared is. So I'll just substitute that. ऊपर मेरे पास कुछ भी change नहीं होगा. 2m pi a b whole squared. L squared की value put करते हैं यहाँ पे, हमारे पास आएगा g m squared a times 1 minus e squared. And now I can use this value of b squared over here, and I can जो मेरे पास well ये है, right? So I can write this thing as well, ऊपर कुछ change नहीं होगा. 2m pi a b whole squared divided by, let's see नीचे क्या होगा. We would have g m squared ऐसे ही, a भी ऐसे ही होगा. And if I divide b squared with a squared, I'll get this thing, right? ये 1 minus c squared. So everything is fine now. From this, मेरे पास what I have is I can simplify this equation as left hand side पे हमारे पास t squared था, right hand side पे हमारे पास 2 का square 4 हो जाएगा. We would have pi squared, and let's see if we make some cancellations. यहाँ से a ऐसे, and it would go up and it would give you a cube, right? और ये b यहाँ से b squared है, तो ये ऐसे b squared ऊपर वाले term में भी है नीचे भी है, तो it would just vanish, right? Or it would just give us 1. So that's it, right? And of course divided by g m. ये m squared भी है, वो इस वाले m squared के साथ खत्म हो जाएगा, right? Okay, let me get rid of these lines now. ये तो कैंसिल कर देते हैं, ठीक है. So well, यही हमें prove करना था ना. This is what we needed to prove, कि t squared is proportional to the cube of the axis, right? And this thing also tells us that the time for the orbit depends only on the semi-major axis of the orbit. There is no dependence of b over here, right? So what that means is that it does not depend on how elliptic the orbit is, right? Or in fact, this is, or at least I think this would be also a good reason to say that we can make an estimate of a circular orbit as well. And so I think that's it, right? We have derived all the 3 laws of Kepler. And again, there are multiple ways for doing this. It's not necessary that जो procedure मैंने use किया है, it is well, it's fundamental. No, it's not. We can look at an example very quickly. We have अभी 8 थे, अब 7 हो गए. We have 7 minutes left. Let's look at a problem very quickly. and it's a very simple one as well. So the problem is something like a हमें होता है कि हम जो है ना कम्युनिकेशन सैटेलाइट्स जो हैं वो ऊपर भेज दें मतलब send them into the orbit so that they remain fixed above some spot, right? And let's say we are doing so in a way that it remains fixed above above some point on equator, right, of the rotating Earth. Earth is rotating, obviously. So let's figure out at what height should the satellite be above the Earth for that kind of an orbit. Right. So, well, what you have to know is for a satellite to remain above any point, then it must be rotating at the same speed as that point is rotating, right? So for our case, the period would be then 24 hours, right? Because that's how it works on Earth, right? So 24 hours, or I can write this in seconds. That would be 86 400 seconds. Okay, so we can solve this problem very easily if we use Kepler's third law, and we can use that to calculate the radius of the orbit. First of all, because that is something that we would need to get the height, right? The height that the satellite should be above the Earth. So, well, ये हमने ऊपर ही लिखा था. So we'll use this equation. And what I have to do is I have to first write this in terms of the height, or I'm sorry, in terms of the radius. So we can make an assumption कि जो हमारे पास a है, it is r. So we can write t squared is equal to 4 pi squared r cube over g m. Now, well, you just have to write this in terms of r. So it would be r is equal to t squared gm over 4 pi power 1 by 3, right? So just substitute the mass of the Earth in this equation, and you would get everything is constant in this equation, right? So what you would get is r is equal to 4.22 times 7 meters. Now note that this is just the radius of the orbit from the center of the Earth, right? But to have the height above the Earth's surface, we just have to subtract the radius of the Earth from this height. And the radius of the Earth is 6.3 times, or 6.37 times 10 to power 6 meters. All I have to do is I'll subtract from this RE, and I would get a height of 3.58 into 10 raised to power 7 meters. So that is the height that the satellite should be orbiting at above the Earth's surface. And this orbit is actually, it's named after Arthur C. Clarke, who even worked on the series Space Odyssey, right? And Arthur C. Clarke is the person who first even proposed this whole idea back in 1948, right? And it's what it's called is, the orbit is called Clarke geosynchronous orbit. Right. So that's it for this lecture. We have 3 minutes left. I cannot derive gravitational potential and all that other stuff in these 3 minutes. So I'll conclude this lecture over here, or in the next one, we'll hopefully see a gravitational potential and all the other good stuff. So yeah, that's it. You can take it from here, Ammar.